Hello guys, and welcome back to my biochemistry videos. It is officially 2:32 a.m. and I am exhausted, but I'm going to try and get one more video out to you guys tonight. Terminology. I think this is the most important thing to grasp from this concept in this entire chapter is the terminology. There are some equations, but they're not going to be prevalent really on the examination, so just understand the terminology and the concepts behind all of this stuff. What exactly is pH? pH is the H plus concentration in a solution. So the higher your H plus concentration, the more acidic something is. The lower your H plus concentration, the less acidic something is, the more basic it is. So a high pH is going to have a really low H plus concentration. It's going to be basic. A low pH is going to have a really high H plus concentration. It's going to be much more acidic. For high pH, think pumpkin frap. For low pH, think of one of my favorite Pokemons, Muck. Okay, how do we determine what's an acid and what's a base in a reaction? Well, how I always like to think of an acid and a base is the acid is the thing that gives up its hydrogen. It's donating its hydrogen. It's the thing that is turning into the H+. So, since we have H2O here and is turning into H+ and OH over here, we know that this is our acid because it's giving up its hydrogen, and this is our base because it is the thing that is becoming negatively charged. So it is the conjugate base, and the thing that is actually giving up the hydrogen is the conjugate acid. Why is this important? Well, from this we can actually find Ka, which the larger the Ka value, the more acidic the substance is, which makes sense because if you look at this formula, that would mean you have a higher H plus concentration in order to get a higher Ka. So if you have a higher H plus concentration, once again, that leads to a lower pH in a more acidic solution. Once you have Ka, you can get pKa by doing the negative log of Ka. Now, one thing to note with pK that is a very important concept, please do note this, this is probably going to be on the exam, is that if the pH is greater than the pKa, the conjugate base is more likely to be present. And I forgot to put the arrow here. If the pH is less than pKa, the conjugate acid is more likely to be present or more likely to be prevalent. So, building off this, why is pK and pH so important? Well, first thing is pH and pKa allow us to solve buffer problems and allows us to understand buffers. And our bodies also need to maintain a stable pH. If we don't maintain a stable pH, a lot of problems will arise in our body physiologically. And once again, this is what leads us to the buffer concept. So what exactly is a buffer? Buffers are mixtures of conjugate bases and conjugate acids that lead to a stable or pH that resists change. And this is very important again because if pH can resist change, it's not going to lead to any of these problems arising in the body, such as GERD or acid reflux or stuff like that, because you just want a stable pH. If you go from a high pH to a really low pH really fast, you're going to have acid burns all throughout your body, unless it's, of course, your stomach that contains acid naturally. But moving on with buffers, the important formula you need to know is right here. And that is pH equals pKa plus the log of the concentration of the base divided by the concentration of the acid. So here's a little example for you to kind of flex your math and brain muscles. If we have a concentration of H2O that is 9.8, and we have a concentration of the anion OH, which is 2.8, and we have a pH of 7.2, what is the pKa? Well, if we plug this in, the first thing you need to do is understand which one is the acid and which one is the base. Once again, acid because it's losing its hydrogen, base because it's the negative conjugate base. It has the negative charge on it. Now, if we actually work this problem out, we can solve for pKa, and we get a pKa that is 7.74. Now then, let's answer a couple questions. Is this an efficient buffer? One thing to know is that if the pH, didn't want to write in highlighter, the closer the pH are to each other, the pH and the pK are to one another, the more efficient the buffer. So if you have pH that equals 7 and you have a pKa that equals 7, that is literally a perfect buffer. That will lead to a perfect buffer. The closer the pH and the pKa are to one another, the more efficient the buffer. Let's answer the next question. Is the conjugate base or conjugate acid more prevalent? Well, the pKa is 7.74 and the pH is 7.2. So, once again, if pH is less than pKa, the acid is more prevalent, which we can actually just look at this problem overall and know that that is true, because look right here. The acid concentration is on the bottom and the base concentration is on the top, and overall we can just visually see that the acid is in higher concentration than the base. So this just proves that concept is 100% accurate. Now, one more thing we need to understand for the examinations is how to read a titration curve. On this curve, where do you think the buffer is actually occurring? Where's the buffering region? Buffering region occurs where the pH is resisting change, which would be right in here, because the pH isn't changing rapidly, it's gradually changing. So this is our buffer region. I want to thank you guys for listening to this video. I know it's this stuff isn't as fun as organic chemistry.